Our first speaker is Hoda Amel from the Manufacturing Technology Center. So Hoda, please come on stage. Your mic up, I think it works.
Hello?
Yes,
yeah.
It works. Thank you. So with a couple of questions before you start, do you mind introducing yourself and tell us what kind of research do you do at the MTC
Yeah, sure.
and why you're here?
So my name is Hoda Amel. I'm an advanced research engineer at the MTC. I work within the additive manufacturing group, mainly looking after the polymer additive manufacturing section of the group. But we also work on all sorts of projects from metals and ceramic and composites, so everything.
And what are you going to talk about today?
So I'm going to mainly introduce additive manufacturing, the benefits of it, the problems that we have with it, and talk about how other sectors are taking advantage of additive manufacturing and how oil and gas probably will want to take that from them.
Thank you very much.
Thank you. So as I said, I'll do a very short introduction into the MTC and the National Additive Manufacturing Center. Then a short introduction into additive manufacturing, and then I'll talk about additive manufacturing in other sectors and the case studies that they're doing. MTC is one of the 6 or 7, seven actually, high-value manufacturing centers. We were founded in 2011 with less than 50 people, I think. We are now up to about 600 employees, 50 of which are working in additive manufacturing. It's not all within the additive manufacturing group, but we cover the whole process chain. Since a couple of years ago, we've become the National Center for Additive Manufacturing, and since 2017, we've become the benchmarking center for European Space Agency. The main aim of MTC, along with other catapult centers, is to bridge what we call the valley of death, which is taking the research from low technology readiness level, which is research that we do in universities, and it's basically just experimental research and lab scale work, up to a technology readiness level that the industry can actually take from us and go and implement it in their own factory. So it's technology readiness level from 3 to 6, and it's basically applied research. So we take it from laboratory scale, use it in a shop floor that we have within MTC to prove and de-risk the application, and then industry can actually take that away from us. We work within 3 main themes. It's the component manufacturing. Additive manufacturing is actually kind of embedded within component manufacturing, but it also has non-conventional machining and net shape manufacturing. We have assembly systems, which involves tooling and fixturing, electronic manufacturing as robotics. And we also have data systems, which is design and simulation, manufacturing informatics, and metrology and NDT. So we basically cover the whole process chain of additive manufacturing, going from material all the way to inspection. We have many partners and members within MTC. These are a few ones that are involved in AM. So as you can see, we have members that are software vendors that we use in our design. We have material vendors, AM processes and machines. EOS should actually be there. They have recently become a member. We have members from post-processing systems for AM, and also from inspection that we use in our metrology lab. So I keep talking about additive manufacturing. What is additive manufacturing? You probably all know it, but I'm just going to shortly go through it so to make sure that we are all on the same page. We have 4 means of manufacturing: subtractive, which is basically taking material away from a bulk. We have formative manufacturing, which is using heat and mechanical force to basically shape a part and make the part. We have fabricative, which is joining some material to actually get the final part out of it. And then, last but not least, additive, which is the process of joining the material layer upon layer to actually build a part. The market for additive manufacturing, additive manufacturing has actually not been around for long. It's only been a few decades, I think, since 1985, which started with rapid prototyping, but it's actually going up. And for not being around for so long, the market share is now £6 billion, which is not bad. 5% of it is in the UK. UK is actually one of the big players in additive manufacturing. So that is why we are investing more in it, and we want other sectors in the UK to actually take advantage of additive manufacturing. And because we see that additive manufacturing is actually going to grow and take more of the market. So speaking of additive, we basically have a data file, a 3D data file that we slice, give it to the machine, and the machine, with different means, actually makes the part from those slices, layer by layer. But it's not that simple. So this is how the media and the ads actually show additive manufacturing to be. It's basically, so you have an idea, give it to us, we design, we give it to the machine, and there comes your product. As easy as that. It's definitely not. Oh, I'm sorry. Okay. So, yeah, you have the idea, you can design it, but then you have to source your raw material, you have to validate your raw material if you want a validated part. You have to decide how you orientate it in the machine, how you support it, how you slice it to get the best properties out of it. Then you can give it to the machine. In the machine, you have to decide how you want to scan it, so how you want to actually melt the powder and join the powder together to get the part out of it. Then there comes powder handling. So you have an explosive powder. How do we handle it? We don't want it to become contaminated, so what do? After the build is finished, we don't want to throw the rest of the powder away because that's a waste of material. We want to save it, we want to recover it, and then recycle it and use it again. Then we have the part, we have all these supports on it. How do we post-process it? We have to remove the supports, we have to heat treat the part, we have to kind of finish the part to get the surface finish that we want, and we have to inspect, measure, and validate the part. And then there comes your final product. So it's a whole process chain, although they say it's as simple as giving the data file to the machine and then getting the part out of it. And actually, the National Centre for Additive Manufacturing helps companies to go from the beginning, which is the material, all the way to the end, which is inspection. So we help the companies through the whole process chain. So what are the pros and cons of additive manufacturing? Because of the nature of the build, which is of manufacturing, which is layer upon layer, we have design freedom. So basically, some of the complexities that we can't actually put into a part because of subtractive or other means of manufacturing, we can gain by additive. We can have a faster iteration from design all the way to the part because we don't need tooling. So that means that we can actually reduce the lead time quite a lot. We have efficient use of material because you don't have a bulk material and getting all of that material out of it to make the part. So that means we have less waste, and we can actually recycle the remaining material and use it again in the process. We can have decentralized manufacturing, which means if we have the data file, we can send it anywhere in the world, and we don't have to actually send the parts to the rest of the world. So if they have the data file, they can actually go and make the part themselves. We can have customization because we don't need any tooling. It actually reduces the cost of manufacturing of one-offs or a few parts. So it means we can design based on customers' needs and get that part customized. We can have increased material freedom, so we can actually have graded material, or we can join materials, have multi-material parts. And we have possibility of remanufacturing obsolete parts. So for example, if in the aftermarket, if we have a car that has gone absolutely out of the market, if someone brings the part, we can scan it and reverse engineer it and make the part again for them. So we have all those pros. What are the problems? The cost of the machines and the materials are still very high. They are decreasing, but it's not at a fast rate. We have limited mass production capabilities, which means we can't actually make a whole volume of part. It takes time, so it's not for producing 1 million parts per week. We have limitations in terms of available materials, so we don't have all the materials in the world available to us. There are research being done to actually get more materials, but that still takes time. And we have a limitation in size of the part that we manufacture, because the size of the part is actually limited to the size of the machines, which are not very huge at the moment. There are some larger machines coming to the market, but that still takes time. And there's post-processing as well. So we don't get a perfect part out of the machine. We have to post-process it, machine it, and it's time-consuming and labor-intensive. So all that being said, we still have, so that says laser beam melting, but that's additive manufacturing in general. Compared to conventional manufacturing, if we have a few number of parts, the cost for conventional manufacturing is actually very high. But the cost for manufacturing a lot of parts actually in one build stays the same within additive manufacturing. So if you have one part, it's very expensive to use conventional manufacturing to make it. But with additive manufacturing, it's actually the same price as if you wanted to make 10 parts or 100 parts. Okay? So if you have one-off parts, it's actually better to use additive manufacturing. It's also the same if you have a very complex geometry. So if you have a very complex geometry, you have so many tools to actually go and manufacture it. But with additive manufacturing, you don't need any tools. So you can add as much complexity as you want to your part for free, which is a huge advantage. There are 7 main processes in additive manufacturing. These are the names that ASTM use. You may hear other names, but these are the standard names that we try to stick to so people get used to them. So the first one is vat photopolymerization, which is basically having a vat of photopolymer that are cured using light activated processes. We have sheet lamination, where we have sheets of material that are bonded together using either adhesive or ultrasonic kind of excitation. We have material extrusion, which is basically having a filament of material that goes through a nozzle and is deposited onto the bed. And we have material jetting, which is basically a 2D printer, but instead of having an ink in it, the ink is actually the material. So it actually prints the material wherever we want it, and then the material is cured and makes the part for us. And we have powder bed fusion, which is basically a bed of powder, and the part is actually formed by fusing the powder using thermal energy. We have binder jetting, which is, again, having a better powder, but instead of thermal energy, this time we have a 2D printer which prints binder onto the material that kind of sticks the material together. And we have directed energy deposition, which is basically the material is deposited onto where we tell it to, and then is fused together using thermal energy. So directed energy deposition is actually for metals. Within the MTC, we have almost most of the systems that I just mentioned. So we have metal powder bed fusion machines. We have DED machines. We'll hopefully have a metal binder jetting machine soon. With the polymers processes, we have material jetting, material extrusion, and powder bed fusion, and also vat photopoly. And we also have ceramic processes, which are mainly vat photopoly and also binder jetting by using ceramic powder. So I'll put in some examples. Okay, so this is an example of powder bed fusion. So you basically have layers of powder coming in, then laser scans the powder where you want it to. It makes a 3D part. After that, you have to remove it. You have supports onto on the part because to get the heat out of it, you have to remove the supports, then kind of polish the surface of the part. This is bead blasting to get a better surface and make sure that all of the powder is out. And then you have to post-process it, for example, putting threads in and other features that you want to add to it. And this is DED, which is basically a CNC machine. It depends how many axes you want to have. And then you have a cladding head. It can have powder and laser, wire and laser, or wire and arc. And powder and arc onto it. So it's basically a lot faster because it's depositing a lot more material onto it. But because it's faster, so that means you have a higher layer thickness, and you can't have as much complexity as you can have with laser powder bed fusion. But it's perfect for making big parts because you can go as big as your gantry actually lets you. And then you can have a CNC head onto it, which mills the part or cuts the part and kind of adds features to it. So as you can see, you can make holes onto it, polish the surface. Okay. All that being said, we can't always, for everything that we need, go and say, okay, let's use additive manufacturing. We can't take all of the conventional manufacturing techniques away and always use additive. We have to ask ourselves some questions before actually deciding to use additive. The questions are all these. So, how many of the parts do I need? That's the main question, okay? So how many identical parts do I need? How expensive is the material? Is the material currently available? Is the part currently obsolete, or is it still being manufactured? Can I get actually more complexity out of the part if I go with additive, or can I get any benefit out of it? Or can I just go and use conventional manufacturing and get the benefit from conventional manufacturing. So it's important to actually ask all of these questions before deciding to go for additive. One of the main things to have in mind is that if you are using additive, it's important to combine it with design for additive. So you can get the best out of additive if you are actually designing for additive. So you can add a lot of complexity to the part, and you can take a lot of the weight out of the part. So that actually gives you, so for example, for these parts, without actually doing the design, you're kind of there, which is the energy consumption. With adding the design, you go down there for energy consumption. So as you can see, you can actually get a lot out of additive by adding the design element to it. Utkasha would later talk about design. So we have a long way to go with additive. We are still here, which is the early adopters of additive manufacturing. I know that oil and gas wants to get there, but I'll talk in a second about how other sections are adopting AM because of all its benefits, although it's expensive. So it's important to kind of make that comparison and see what works for your section. So talking about additive in other sectors, first thing that comes to mind is aerospace. Additive is perfect for aerospace applications because you have not many parts. Most of them are custom to the aircraft. You can add complexity to the part, take a lot of weight out of it by design, and it's basically perfect. Aerospace is actually one of the largest users of additive. They are making a lot of metal parts and a lot of polymer parts that are currently flying. So many of the Airbus and Boeing parts are actually kind of being additive manufactured at the moment. And the use of additive manufacturing has grown in 2016 by 1.5%. So here you can see, as I said, you'll always have supports. So you have the supports, you have to remove them, you have to surface finish and everything. But these are some of the examples that are being used in aerospace and aircrafts. This mainly is the Champion because it has gone on a flight. That's a front bearing housing of an aircraft engine, and it has flight and it successfully finished the flight. So we are very happy with it. It was actually manufactured in MTC. Another user of AM, which is again perfect for them, is medical sector. So they have adopted AM for different things. They use it for prototyping, so for example, using for surgeries and stuff, but also they use it for implants and dental applications as well. So you can see a hip implant there. They use it for, instead of very heavy casting, they use additive to make light but very strong parts. And also for dental applications, it's again great because you have a lot of small parts which are customized, so you can actually fit them all in a bed and get them out without any extra cost. And then there's automotive. Automotive was one of the first sectors to start using additive as rapid prototyping. They have not caught up as fast as other sectors with additive because of the large volume of parts that they have. So they have big parts and also a big massive part. But they are starting to actually take on that for example, Formula 1 cars or for customized parts, customized cars, which you don't have many of them being manufactured. But they are also looking into expanding additive use for aftermarket use. So if a car is going out of market, you can still go to the reseller and kind of have the something that you want for your car manufactured on the spot. And one last example is our Reclaim project, which was basically remanufacturing and repairing of really big parts. So the way it worked was actually we had a CNC bed. In the CNC bed, you have a scanner. You can put a part that has been damaged, for example, like a bearing or a rail sector, into the machine. The machine would scan the part to see where the damage is. Then a cladding head would come out and clad material onto that part to actually add material to where it's been damaged. And then a CNC head would come out and kind of cut the material to get it the shape. So that's basically is being used for repair right now, and a company has acquired the system, and they're using it now. So that has gone into production. So that is combining additive with CNC machining, which is actually kind of getting use of both of the systems and their advantages, and it's basically having less material waste, but having the precise and repeatable properties that you can get out of CNC machining. And that's basically it, really. So I hope you have got a good idea what additive manufacturing is and how you can actually use it, have an idea of how it's used in other sectors, and hopefully have started thinking of how you can use it in oil and gas. So thank you.